In this we do problem, we're going to take the molecules that are shown above, alkane, alcohol, ether, amine, and ketone, and try to figure out which ones would form hydrogen bonds with water, which ones would form dipole-dipole attractions with water, and which ones would form London dispersion forces only with water. So we're going to go ahead, I'm going to create three groups. We're going to call this first one hydrogen bonds, and then we'll say dipole-dipole. And then we'll say LDFs for London dispersion forces. Go. When we're talking about hydrogen bonding, we're going to be looking for hydrogen covalently bonded to either a nitrogen, an oxygen, or a fluorine. So we're looking for NOF. Uh, if we look at the alcohol, that's the first place I see a hydrogen covalently bonded to an oxygen. So that would be able to hydrogen bond to water. So I'm going to put alcohol into that category. Then another one that I see down here with the amine, I see a hydrogen, two hydrogen covalently bonded to a nitrogen that would also be capable of hydrogen bonding with water. So we'll put the amine down in that category as well. I'm going to switch over to LDFs because London dispersion forces should happen between molecules that aren't capable of hydrogen bonding and really tend to be nonpolar. I only see one of those, and that's my alkane. So I'm going to put my alkane here under LDFs. The other two that I have left have a partially negative end and partially positive end there on my ether. And then when I look at my ketone as well, I see a partial negative end and a partial positive end where I have my carbon and hydrogen. So under dipole-dipole, we're going to add ether and we're going to add the ketone. So now that we have those sorted out, let's go ahead and take a look at question 2. Question 2 says draw a particulate model of two alkane molecules. So my alkane molecule is right there. Draw how the strongest intermolecular force present acts between the molecules. What are the names of this force? So we already said, I think, that that's going to be London dispersion forces. The tricky part here, honestly, is probably drawing the picture. Let's do this way because they say particle models. So you could do this a couple different ways. You could do carbon, carbon, carbon. I'm going to draw it the same way they have in the picture. CH3, CH3, they have that way. And then we'll do another one just right below it. Carbon with the hydrogen, CH3, and then the other CH3 over here. Kind of looking at this as a particle, London dispersion forces are going to be when a um, instantaneous dipole is created because there's a shift in electrons. So I'm going to say with this one, we've got a partial positive at this end and a partial negative due to the shift in electrons, which would cause a partial positive on the molecule underneath of it and a partial negative on the other end. So it's kind of this instantaneous shift of electrons that's going to cause attractive forces between these instantaneous dipoles, and that's going to be our London dispersion forces, or LDFs. That's probably the best way to show this. Now, the one underneath of it says, draw a particulate model of two ether molecules. Draw how the strongest intermolecular force present acts between the molecules, and what is the name of this force. So for ether, we said it fit under dipole-dipole. So for the ether, we've got an oxygen here with its lone pair and a CH3 and a CH3. And so we know we've got a partial negative end, a partial positive end there. So if I was going to draw another ether, I'm going to go ahead and draw it this way. CH3 CH3, my lone pair. And so again, marking my partial negative end and my partial positive end there, I would see dipole-dipole attractive forces between the partial positive end of one of the ether molecules and the partial negative end of the other ether molecule. The difference here is that this is a permanent dipole. This is not something that just kind of happens because there's a shift in electrons. Dipole-dipole is when there's a permanent partial positive and a permanent partial negative end. So I think that's a good picture. You could draw that a couple different ways. That's it.